Okay, good morning, everyone. We have an action-packed lecture for you today, and it's all new content. And I think the interesting part of this lecture is we're not going to cover just azaindoles, but rather the furopyridines and thienopyridines. And that's where really furans, and as I promised you before, that's really where furans and thiophene shine. Modern medicinal chemists are not making a lot of benzofurans or just parent furans. They're not making a lot of thiophenes or benzothiophene. It happens on occasion, but in the modern era, they're taking those 5-member ring heterocycles and they're fusing them onto pyridines. So this lecture combines everything you already know. You already know how to make furans, you already know how to make thiophenes and pyrols, and you already know how to make pyridines. So what happens when these two are fused together? This is our first example of where we're systematically going to go through fuse types of heterocycles. And the logic you need to know for this is very simple. All one needs to do when they have a fused system, such as this here, is take one of them and pretend it's a benzene. And then take the other one and pretend it's a benzene. If you do that, everything is easier. Now, the general rule of thumb for azaindoles, as you see here, is about 70% of the time, you're going to start with a pyridine and annulate onto that a pyrrole. For thienopyridines, it becomes more popular to annulate the thiophene. And finally, for pyridines, almost always, you're going to be annulating the furan onto the pyridine. But these are kind of my rule of thumb over the past many years of consulting. It's definitely not a guaranteed strategy. And we're going to see today many examples of where those 5%, 20%, and 30% cases are really strategic. So if you take, for example, a compound like a thiophene like that, when you think of the retrosynthesis, you're going to be looking at it from the vantage point of one of them possible retrosynthetic analyses is that, or the other possible retrosynthetic analysis is that. Now, we haven't learned quinolines yet, so some cases today you're going to see a sneak preview of what we talk about next week. But that's conceptually what you're going to do every time you think about which one to annulate. And you already know the answers to many of the problems we're going to be going through today. So hopefully we can breeze through a lot of these problems of the day and case studies in a rapid fashion. I should also mention that there's some useful reading material for you. So there's a chapter we wrote a few years ago on the 5-6 fused heteroaryans, and in those is a list of all the rules that one could possibly want to know for all of these. And the other thing I'll mention to you is in lecture number 1, we talked about aromaticity as a guide to retrosynthesis. And many of you may have been confused by what in the world I meant by that. And as you'll see, these rules correlate pretty well to that in terms of the degree of aromaticity of pyridine, which is very close to relative to the other heterocycles to benzene. And so that's why these rules are almost always starting with the pyridine and annulating on, because the pyridine usually looks better as the benzene ring rather than the thing that you disconnect. Things get very confusing when we start talking about naphthyridines, where you've got 2 pyridines attached to each other, and then that's when things get kind of complex and the retrosyntheses kind of become almost in many cases equally simplifying. So with that little introduction, let's begin with furopyridines and all of the various isomers of furopyridines. And we can do this in a rapid fashion. I'll go down the list of people and ask for your train of thought. So Sunghan, maybe you can start us off this morning in thinking about what strategy you might very rapidly go towards.
I think I will do something like the rock condition.
Awesome. Perfect. You know, that makes a lot of sense to start with A and then annulate on B. If we were to do the B annulate on A, gee, that would be a kind of weird thing you want to do there, because you need something like this, and then you need to somehow append onto there something like that. It could work The only problem is we learned that these types of aminofurans are not very stable without an electron withdrawing group. So that would be a big warning sign there. And then you have to actually make that furan, which is going to be a lot more steps than simply buying iodopyridine or simply making it. So that's why this seems very intuitive and very fast. So with the same logic in mind, Nathan, what are your thoughts on problem B? Do you see any groups in problem B, any particular carbons that signal something special to you?
Is there a hidden cyanide in there?
I love that. That is just great. Look at that. Hiding right there. That sneaky little cyanide. And what are we going to do with that cyanide? Let's put it here. We need something.
Oh, so we would need a nucleophile next to the ester.
Exactly.
Yes.
Perfect. And so that can usually be made pretty easily from something like this. Treated with base and all done. Brilliant. All right. How about Brendan for C?
I think you could probably do a similar approach to the first one, where maybe you have the benzylic alcohol protected, and then you treat that with, you have the same sort of Sonogashira starting material with just TMS acetylene.
Okay. You'll need to come up with a route to this. That is sort of going from A to B. Can you help me if I do want to do the B to A? What would that look like? I'll make your life a little easier and put as a placeholder here an ester, because we know we can reduce that and turn it into the benzylic alcohol. So what would that look like?
So you want to annulate the pyridine onto the furan.
Yeah.
That looks pretty tough.
Well, it would require something like this. So I predict that if one were to make this furan, a mitofuran, treat it with acid, and then immediately dump in this aldehyde, that annulation would work.
Okay.
So you end up with two routes that you're going to be, going to SciFinder and basically searching for either your prep of this. You'll find out this is easily available from a courteous rearrangement. You'll then look up your prep for this, which probably comes back from something like a nicotinate. And you'll worry about selective iodination there. But that will be your thought process. And probably what you'll come up with at the end of the day for this particular compound is that the annulation route is pretty decent to start from a mitofuran as long as you liberate it in situ. You don't want to have that aminofuran lying around very long.
Right.
Hey,
Okay.
Phil,
Yeah.
if you had just a methyl group there and you treated that with NCS, would you get chlorination first at C3?
If you were to take it's a good question, Tim. So if you were to take a compound like this and treat it under radical halogenation conditions, you have a good chance of the radical halogenation conditions going here. However, in practice, you have to be careful because this position wants to halogenate really well. So you just have to be really careful with your conditions to make sure it's radical based and not electrophilic based, so you don't get that competing halogenation at the furan side. Yep.
Well, thanks.
Great. All right. How about Tawe for the next one? What would you do? And if Tawe is not here, how about Ellie?
Yeah, I think that you could also do the TMS alkyne with like a Larock disconnection.
Oh, I'm so happy you said that, Ellie. Oops, sorry. Okay, so that is good. As long as we can find a way to distinguish, you'll need to order or find a way to, probably will be fine, to put a bromo or an iodo there to make sure you get selectivity between this halogen and that halogen, but it should be doable. If you wanted to do the B to A, you could imagine this unit that you see here is basically an isocyanate hiding. And so you could imagine that if you were to generate that compound, upon heating, that compound would then cyclize, which after treatment with POCl3 would give you the product. And this compound simply comes from a Curtius rearrangement. So you would hydrolyze that ester, do the Curtius, heat it up, and out would pop the desired product. You would usually treat this with something like PPA, and you would expect to see some isomerization if you're worried about the EZ there. So that's another viable route that people have used to make such systems. You might look at this and say, hey, Phil, I would never do that. I want to do the Sangashira. That's fine. The Laroc is fine, but you must have that disconnection of B to A as an available one to you if you cannot execute on the A to B based on your substituents on the ring. So great, thanks, Ellie. How about this next one, which is missing a ester group here? Sorry about that. And so this next one, hopefully Alex can help us out with. Would you do A to B or B to A? And what would that look like? And if Alex is not here, how about Noor?
Intuitively, I would say A to B, considering that you have.
I want your intuition. That's great. And so for your intuition, that would require what?
I think an easy way to do it is metalon type. Oh, wait. Mm. Yeah.
Okay. Now tell me this, Noor. Now that we've drawn that compound out, do you find it to be simplifying?
No, you have to put a lot of substituents on the pyridine.
A lot of stuff going on there. That's right. So we tried A to B, and that's where it got us. That's great. Your intuition was A to B because it feels better. 70% of the time, or
Yeah.
95% of the time, we taught you the furopyridines are going to be made that way. So that's great. Well, now we have to go back and think about B to A. And if we think about B to A, something magical happens. Do you see it?
Well, I guess I don't know if that's right, but I might try to construct the 1,5-dicarbonyl for the pyridine.
That's a great idea because it leads us to the answer. That is your 1,5-dicarbonyl hiding. And the way to execute this would be to simply take this compound, stable because it has an electron withdrawing group on it, plus that. And under the right conditions, we'll learn about this in quinolines. You should be able to get the annulated product. So if you have questions about regiochemistry, that's a good reason to come to the lecture on Monday, because when you see the compound like this, you can basically view it the same as if the proposed question was this.
I have a quick question.
Sure.
Can you to make the 2,3 bond, can you do sort of like a Michael addition, or would that go to the ketone? Like if you do electrophilic aromatic substitution with the furan?
So if you do electrophilic aromatic, you're saying instead start with something like that. And would a nitrogen nucleophile add in here?
No. So to make the 2-3 bond, so between, so you'd still have the amino group present.
Well, that's what we're doing. That's exactly what we're doing. So that going here, and that is going there. So we are doing an electrophilic aromatic substitution exactly as you recommended.
Right. I mean, can you, like, if you start with the Michael acceptor instead of the diketone, would it cause a regiochemistry problem?
It's a that is a viable. Yeah, you could think of this one instead. I see what you're saying.
Like, would it have a preference for the ketone or the 4 position?
You'd have to modulate the conditions and find out, but I suspect that this is a good disconnection. I expect that the regiochemistry would be right in this case.
Okay, thanks.
Yeah, either one would be fine to propose. Great. Awesome. All right, let's take a look at a case study. This one comes from a few years ago from a former postdoc, Kyle Eastman, who was at VMS at the time, working on HCV polymerase inhibitors. And the synthesis begins with a very simple pyridine starting material. And what we need help with is guiding us on the various steps involved in converting this compound to the product. So let's get some help from Nick, wherein we're going to take this compound and treat it with NBS and need some advice on where you think that bromine is going to go. And if Nick is not here, we can ask Feng.
I think if you treat it with NBS, you will get the bromine on 5 position, a bromide.
Awesome. And then that BBR3 is going to do a good job of lopping off that methyl group. And then maybe keep going, Feng. So after we treat that with NIS, what happens now?
So it will be ion donation on 3 position, I guess.
Awesome. And then we know what's going to happen next.
Is some Nagashira, and then
I want to get ahead of myself. All right, we've got the Sonagashira to take place. We've got our arrow where it needs to be right there. And then we're going to treat this with NIS. Feng, you can keep going.
If you treat it with NIS, I think the furan ring will be ion donation on the C2 position.
Well, the label here would be 3.
Oh, okay, C3 position.
Right. And subsequently, we'll need to treat this with a set of conditions that involve palladium and carbon monoxide.
So I think based on the reactivity, the carbon ion bond will be cleaved by palladium, and the carbonyl insertion, and then form the amide bond.
Brilliant. These types of intermediates, thanks, Feng, these types of intermediates are what you see in the real world all the time. Med chemists love them. We're going to see an example of this in a moment when we circle back to problem of the day number 1, which I'll get to in just a second. This is a kind of intermediate that you see quite a bit, and you take advantage of the enhanced reactivity of iodine versus the bromine versus the chlorine, and that's how we get selectivity. So subsequently, when we do the Suzuki, Feng, are we going to get Suzuki to take place at the bromo or the chloro?
Of course, you will get the bromo displacement.
And finally, we have 1 chlorine left, and that's how we get to our product. So using the logic we just saw here, let's circle back to problem of the day number 2 that we skipped on purpose. So now, problem of the day number 2 asks you, based on what you have just seen, to opine on a good strategy to get us to diversity in the following order. We want to put R1 in first, then R2, and then R3. So we need a good strategy to think about how we might do that. What would be the knee-jerk response, Kelly, for a medicinal chemist, you think, in putting this together? Can we come up with some sort of trihalogenate intermediate or something like that? I don't know.
Yeah, can you also use some Bushira type from a, I guess you would also need maybe like a bromine present in your pyridine.
Something like that?
Mm-hmm.
Yeah, that's a great idea. Now, when we do the coupling, the cross coupling, this is a typical consulting problem. Where is it going to go? Here or here? How would you go about answering that question?
I think you'd have to do some hand waving.
No, you don't need hand waving, but it does involve a hand.
I think it would go at the 4 position.
I think it would go at the 4 position. So we learned away the so-called handy rules. And that was a handout given to you, I think, in lecture 2. And let's look at the handy prediction. So all we have to do is go to ChemDraw, super easy. And when we go to ChemDraw, we see that, oh, here's our 2 positions. The proton is 8.6 for this one, 7.2 for that one. So we know that that one is going to go first. So you're in deep doo-doo. So this is not a viable, you can't recommend that in a consulting session. You're going to have to do something different. So what might be a workaround to this problem? Because we could take this compound, we could easily iodinate it. We could do our first coupling there, that's fine. But our second coupling is going to go here, and that's not good. We want it to go here. So what's a way around this?
Can you install a blocking group first? I guess that would be kind of steppy.
That would be kind of steppy. How about if you just use the innate reactivity? What if we just said, you know what? Let's scratch that idea. Let's just start with something that has only one of the halogen atoms. We do our first cross coupling here. Now, Kelly, we have R1 in there. We're good to go on R1. We now need to put R2 in. How would you do that? And let's say, yeah, how would you do that? Would you have a problem?
Can you brominate instead? So then that would react first in Suzuki?
Okay, I love that. That is a great idea. So what you're saying is brominate here. And the problem you're going to have is, wait a minute, you've got this position, which is super active. But wait, you can fix it. So instead of doing this strategy, we're going to do a Laroc. So we're going to take your starting material. Put some big old bulky silyl group on there. We're going to end up with this. And now we have your blocking group that you mentioned before, but in a little bit different context. Now, do you know a way that we can install something here from lecture 3, maybe?
Can you use halogen dance?
Well, we don't need to dance anything yet. There's no other halogen. And you can't dance a chlorine. Chlorines don't want a tango.
Would bromination just go to that position directly?
That would be probably not the most easy thing. Is there a way to guarantee you get it?
I don't know if N oxide would help.
That's an interesting idea. So if you wanted to, you could make the N oxide and then put something there. That is a good strategy. Might work, and it's protected by this TIPS group, so you might be okay there. Is there anything else you can do that we learned for functionalizing these? How about just deprotonation?
Oh, okay. Yeah.
Right?
Mm-hmm.
So that should be fine too. So you can either use N oxide, or you can use something like Bewley or LDA, something like that. This position is blocked, and that will let you put in your iodide or bromide. And now we can do Suzuki all day, Buckwall, whatever you want. That will go selectively here. That puts R2 in, and then the final sequence is just putting your last R3. There's no other halogens to worry about. And whenever you want to remove this, you can with KF. That'll come off, or even some HCl will have that silyl group come off. Does that make sense, everyone? Yep. That's how a med chemist would do it. Now the process route, of course, would be quite a bit different, and it would depend on what R1, R2, and R3 happen to be.
Hey, Phil?
Yeah, what do you say there, Tim?
Can you just have the bromine in the 4 position pre-installed before the Laroc, or would you have like the competitive Laroc, would it not favor the iodine?
It would favor the iodine. So another possible, as long as you've got a good route to this compound, that's another possible answer, as long as you've got a good coherent route to that compound. The only potential issue is, whether the NBS step works here. And yeah, you could Psi-Funder, it probably is known. So, if you took this compound and you NBS it, you may in fact get bromine there, and that might be a fine solution. In the event, the people that did this work chose to do it in a stepwise fashion, but if you drew that on paper, you probably would be okay. We couldn't really take any points off. Yep.
Hey, Phil.
Yep.
Going back to the N-oxide formation, if the furan were replaced with a pyrrole, would you have issues there? And like, what kind of factors would you consider when forming the N-oxide?
So if you're going to make an N-oxide with an azindole, you can do that. It just depends on what the substituent is on the pyrrole part of the azindole, so that you don't get oxidation of that 2,3 pi bond. But I've seen people make N-oxides on azindoles, and it can be done. It just often depends on the substituents, but you should be okay. It's definitely a viable suggestion. Okay, great. Any other questions?
Super quick one for on the forward route we did right before this problem with the NIS and BF3 ether rate. What was the ether rate for? Okay.
Coordination there, and probably also activates the NIS to make it more active. So you can activate succinimides with tosic acid, Lewis acids. It makes it even more potent of a electrophile. Okay, great. So let's move on to, we've finished furopyridines. Let's move on now to thienopyridines. And we're going to do the same basic exercise, and Simona has happily volunteered to help us with this one.
Right.
Are we gonna, which way are we going to go?
I would open the pyridine because I'm looking at that hydroxyl group and wondering if you could tautomerize it and then use the inherent reactivity at the C3 position of the thiophene.
So it's very likely that you may not even need to attend Monday's lecture, Simona, because you have it exactly right. This just comes from an amino thiophene plus, and you know what? The answer would have been identical if I had drawn this compound. You see that?
Yeah.
So by doing that exercise of pretending one of them is an aromatic ring, it was a great idea. Alternatively, if we went the opposite way and we thought about starting with B going to A, look what a mess this would be. Does everybody see that? Which one do you want to start with? A tetrasubstituted pyridine, or simple materials, dump and stir and heat, and you're done. So The exercise of doing both annulations is a great one. It takes you only 15 seconds to do both of them. And then you immediately know, at the very minimum, you're going to get partial credit on a test if you just show that retrosynthetic analysis. You don't even need to show the forward route. Just show that you thought about the right disconnection at the minimum. And on a job interview, that's all they want to see. It's enough for you to just say, oh, I would break up the pyridine and annulate onto the thiophene. They're not going to ask you for reagent conditions. I just want to see how you're thinking. All right, great. So Simona, that was so easy for you. Maybe we should just keep harping on it. Do you think you can help us with this one too?
Sure. Can you do SNAR to install the phenol? Oh, sorry. I guess that doesn't really matter. Disconnection wise.
It does. It does. Well, you simplified it. Let's keep it like that.
And then I guess when I see that chlorine, I'm thinking you might have used POCl3 from like a pyridone. And then I'd want to open up that pyridone. I guess in one of the lectures we used like a acyl ketene intermediate.
Simona knocking it out of the park, as usual. Why was that your knee-jerk response?
Well,
Let's
I
look
guess.
Let's look at the other way. Why do you not like that?
Sterics.
Well, it's trisubstituted pyridine. I've got to worry about how to put these various groups in a selective way. I'm going to have to do an SNAR selectively with the two chloros here.
Right.
It's just much more complicated. It's a bit of a mess. Whereas what you did was very logical. There was no step that I could catch you and say, wait, how are you going to make that? Everything just, it fell like a waterfall. It was perfect. Brilliant. All right, let's move on to the next one. And for this one, maybe Nguyen can help us with this.
Well, I would think up the nitrite group and
so you located that immediately, didn't you?
yeah.
And so why don't we think for a moment on what a good candidate for a substituent maybe to remove might be. Can we look at this thiophene and just get rid of it?
Yeah, like I guess we can do cross-coupling with that.
And then you noticed a great disconnection, which is that. And in practice, this might be surprising to you, the X that they actually used here was NO2. And this comes back from that's cheap and easily available from that by way of first bromination and then Sandmeyer and then nitration and then Sandmeyer will get us to this compound. We can then do a addition onto that bromo-nitro compound, cyanation, and we get to the product. So what would you go back to SciFinder to look for? You would basically look for a viable candidate like this. And if you wanted to, you could even on paper propose something like this. It would certainly be something that I would search for first. Okay, and that would bring you down this road of functionalizations that's in the literature, but certainly if you were to put on a test, that you wanted to put this compound and you wanted to add it to a Weisselman or Gawal type donor, that would be fine. Now let's take a look at the opposite route.
But then so the sulfur just added into the pyridine and kicked out the nitro group?
Kick out the nitro group, correct.
Oh.
Yep, ipso substitution and loss of the nitro, that can happen. But that's the kind of thing I wouldn't want you to memorize. It's a special case. This is the one you need to know.
Okay.
That's the one worth remembering. The other one that's a bespoke type of reaction is one that you would find when you actually started looking at literature. But your logic, the point is, you identify the nitrile, you remove the air through a Suzuki. Once you get there, you're in much simpler land. You're in this land here. It's a lot simpler to think about this compound than it is to think about the starting material, or alternatively, a lot easier to think about that than thinking about, you know, how you would necessarily annulate on the equivalent of something like that. That's not so simple, is it? Right, so you make the two disconnections, you see which one feels right, and almost always the disconnection that brings you back to a nitrile, just as you identified in the first 10 seconds, is the one that's going to get you there. Awesome. All right, how about some radiolabel? We need a radiochemist, and we have a few of them on this list. Tim, you're a radiochemist, so can you tell us how to make this compound?
Yeah, sure. I actually made this one similar to the one I made above, but what I started with is I had the A ring with chlorines at the, or halides at the C3 and 5 position. And then what I did is I cross-coupled cross-coupled the aromatic on there, that first, or the phenol. And then from there, what I did was took the alpha ester, alpha amide, and then condensed on DMF, DMA, or I guess the dichloroketone. And my thought was like, if I have those two directing groups, then I should be able to lithiate at the thermodynamic position, and then that would snap close.
Where is the sulfur coming from?
Oh, sorry. I meant the having an alpha, like the sulfur alpha ester. I don't like.
Doesn't feel perfect, does it?
That is what I was trying
But
to
you're
do.
very close. You're very close. Let me ask you this. If I just told you I'm making this compound, just this, would you have had an easier time? What would you have said that came from? Just this, benzothiophene, straight from lecture, whatever it was, 5. Forget about the pyridine. What would be a good disconnection here? Do we remember Feiselman?
Yeah.
Feiselman tells us we need this.
Aldehyde.
Yes.
But I was trying to find a way to install that aldehyde at the last step, which is why for the first route I did the condensation again.
Well, either way, it's still not the last step, because then you need to make a highly volatile radioactive material. Don't want to do that. If I can avoid it, I don't want to do steps to make small molecules that are volatile, or, you know, I'd rather just take the compound you proposed. I don't need any cross coupling at all. I can use, we know we can lithiate there, got 2 directing groups. This is super activated. We can lithiate there. We can quench with DMF. We can add in no more cross coupling, just add in SNAR. And look what happens. It becomes the same problem as this one.
So instead of that intermediate that you circled, if you just took the or the ester with like a sulfur at the alpha position and then put that on the chlorine at C3, would that make it easier to do the condensation, or just not at all?
You're saying add the sulfur nucleophile before I do the DMF lithiation?
Yes.
The problem with that is just now I've got two acidic groups in mind. I've got the alpha to the sulfur, and I've also got the, the pyridine anion. And I would worry that you would get actual alkylation at the carbon in between the sulfur and the ester rather than the carbon of the pyridine anion.
Okay.
So that's why I do it in this order. I treat this with labeled DMF. I got this compound, which I can then add, and I, by the way, I can do it at this stage, or I can save radio label steps by first doing my SNAR and then treating with DMF label to put this compound, get that compound directly. So I have one radio label step, and then I immediately take this crude material and treat it with my Feiselman donor, and I'm done. Really only have to traverse through one radio label step doing it that way.
Okay. Thanks.
But you captured it right away. That's the intermediate we want. All right, super. Thanks, Tim. So we've got this interesting little kinase inhibitor now, and it is a pyridothiophene, and we're going to need some help putting this thing together. And perhaps we can lean on Daniel to help us out with what in the world do we do with this? Some disconnections that you think we can immediately, get rid of some complexity, get rid of some functional groups, side handles. What can we just strip the molecule of right away?
Yeah, so my first thought would be the thiofuran aromatic group, so that could be brought in through cross-coupling.
Awesome. Anything else we can get rid of really quickly?
The C4 carbon of the pyridine and that nitrogen.
Cross-coupling or SNAR,
Yeah.
gone. It's all gone. So let's draw what intermediate we're left with. I didn't leave myself enough room. That compound, great. That should lead us to the product. So how do we make this? What's the first thing we'll get rid of now based on lecture number 3? When we talked about CH lithiation, we had a retrosynthetic hierarchy tree of things that go in early and things that go in late. What was one of the things that you want to get rid of at the early stage of retrosynthetic analysis? Iodine, chlorine, or nitrile?
I would say
I got to get rid of something. So what am I going to get rid of?
I guess the chlorine, because that's pretty activated there.
Well, the chlorine will come later, but the first thing I want to get rid of is the iodine, because I know I can easily.
Yeah.
Yes, I can easily deprotonate there, and all is good with the world. So that's clearable. And then I'm going to do exactly what you said, and I'm going to remove that chlorine. And that brings us back down to that, which is looking very similar to what Simona just taught us a little while ago.
Would that
POCl3, we can convert that ester to a nitrile. This is POCl3. And then we have AB. And Daniel, based on what Simona taught us, do you see how we can make that pretty quickly?
she treated it like an A. She had started out with the A ring system, the thiofuran.
So she pretended it was nothing more than a quinoline.
Mm-hmm.
That's it. Pretty easy. Does that feel intuitive to you, Daniel, now that you see it? Feels right, right? Okay, good. Let's move on to this interesting little protein kinase inhibitor from GSK. And for this one, luckily we have Carter, who is going to help us out in thinking about how we might put this together pretty quickly and thinking about it from a medicinal chemistry standpoint, because this is a BMCL paper. So what groups do we think we can excise out of here pretty quickly?
I think you could remove both extraneous arrow groups.
And that leads us to something like this. Now we need to think about halogenation here and halogenation here. So which one do you think would probably be smarter to put in retrosynthetically start with and retrosynthetically put in later? So I'm gonna give you two options. I'm gonna say, do we start off with something that will lead us down a path where the AR is here first, and let's say a bromine is here later? Or do we have the AR here, and then let's say then bromine is here?
My instinct would say that it's easier to brominate C3 to the thiophene.
So you're saying it's easier to, yes, okay, so that would mean probably that's the correct answer. And that leads us down a path of thinking about this compound. Now the question for you is, we've got this AR in place. We clearly can't have two bromines there. So what strategy might we use to figure out whether we're going to get bromination here, here, or here? Is there any method we have at our disposal, a priori, that doesn't require breaking out a supercomputer to tell us where the halogenation would go? I mean, I think it might go here. I'm not sure. Do you know? You're in a medchem group right now, let's say, Carter, and your colleagues are bashing your idea, saying that's never going to work because you're never going to get the halogenation in the right spot. What do you tell them?
I guess I can't pull out my little handy.
Oh, you can pull out, sure you can. That's exactly what you can do. You can say, hey, but you folks forgot this key paper that we covered in heterocycle class, namely this ChemDraw trick. Remember this paper? We covered it, I don't know, lecture 2 or something like that. All you need to do is go to ChemDraw and predict the shifts. Remember that? And so now all we need to do is go to the ChemDraw and let's see what it says. Okay, we've got the position here we're worried about. We've got the position here, and we've got the position here. Which is the lowest one?
C2 to the...
There's your 113. This is 127. That's 148. So while they're complaining about your idea, you open up ChemDraw, you do the prediction of C13, and you tell them, I am positive my idea will work. And that means this is a viable starting material. And so we can then keep going along this line with very high confidence that our NBS step is going to give us the correct product. Now we need to move backwards again, and that leads us down a road towards this brominated pyridothiophenol. Much simpler than the starting material. So thinking about how we might make that, there's a few ways to think about it, but we could use what we did in the earlier problem of the day, which is to imagine, well, this NH2, it could represent a nitrile, but it might also just represent the product of a POCl3 followed by ammonia. And once we get to something like this, things become kind of simple, because now we can use what Simona taught us before, which is just to pretend it is like a quinoline, in this case, an isoquinoline. What do you think of that, Carter? Feels good?
Yeah.
Great. Any questions? Okay. Let's take a look at azaindoles now, the promised topic of this class. Now, in the book, there is a chapter on azaindoles, and part of that, you'll find this kind of Consumer Reports-like depiction of what types of syntheses might work well for each of these. And in the book, you can learn why certain types of fissures, for instance, may not be good, or certain types of Bartoli's may not be good. But in general, you can basically take all of what we talked about in the last lecture or the lecture before when we talked about indoles and apply it to azaindoles, because you're just going to pretend that the pyridine is an aromatic ring. So you're just going to pretend you're dealing with an indole. And then in the other instance, you're going to pretend that you're dealing with a pyrrole, and you need to fuse that on. And as I said before at the beginning of the class, roughly 70% of the time, you're going to be taking an azindole and you're going to pretend that it's simply an indole. And then 30% of the time, it happens a lot, mostly in process chemistry, that's a big clue to you. Mostly in process chemistry, they will often go default back to a pyrrole that then is annulated to give you a pyridine. And the strategic reason for that will be clear in the next few minutes. So I encourage you to study that chapter of the book. We include it here in the notes because I know a lot of the outside folks don't have access to the book. So let's take a look at problem today number 4, which should be very much like shotgun answers because you've already learned all of this already. It's the only thing that is different is I threw a nitrogen in there, but it shouldn't matter. You'll see it shouldn't matter at all. So we've got a C7 substituted indole basically. And when you see that, that's a good signaling element for what, Junchen?
For Laroque.
Sure, we can think about that. Is there another way we can do this?
Fisher, maybe.
Sure. Or you might just find when you use check SciFinder that this compound is cheap as chips and do a Bartoli. Any of those are fine. Questions? Okay, we need a radiochemist. Where's Tiffany? How do we make B?
Can you do a Fisher?
Now, if we were going to do, first we need to do something with this benzylic amine. What do you think is a good sort of placeholder for the benzylic amine?
Cyano.
Sorry, can't hear you. What do you say, Tiffany?
Oh.
I need to put something here. I'm not going to want to carry that benzylamine through the whole sequence, am I?
No. Halide or cyano, something that you can reduce.
Cyano is a good idea. Sure. Okay. All I do is reduce it off at the end. And then you said you wanted to do a Fisher, but keep in mind, I've got that compound, I've got that radio labeled here. So the other issue with a Fisher might be that how do I control the regioselectivity of it going here versus here? That's the tricky little thing about an azindole. If I were to look at this as a regular indole, your idea, Tiffany, would be pretty good. I couldn't complain about it if it was just this, because I don't have any regiochemistry problem, do I? But here, Tiffany, I've installed that annoying nitrogen, and now regiochemistry will be your big problem as a radiochemist. So I need to go back to the indole synthesis chapter and think about a way to ensure that I'm installing that one carbon there with the proper regiochemistry relative to the nitrogen. So you have another idea for us besides Fisher?
Madelon? Would that give selectivity?
Something like that, treat that with base,
Yeah.
close it off. Yeah, I think that would work. No problem. You could also imagine Lime-Gruber type. Either one of those is decent. Sure, great.
How many steps would it take to make that, the nitro? Pyridine?
I don't think very many. You probably would be able to just get it back from perhaps nitration of this is how they make it. And then conversion of that to the nitrile. And that probably, I wouldn't expect no more than a couple of steps to make that compound, or it might simply come from direct nitration of the pyridine. So because your radiochemistry, the number of steps doesn't matter on the cold material, so you're fine. Super. How about C? And for this one, either Tanner or Chuang. And if they're not there on the call, how about Debbie?
Yeah, I think we can disconnect between the pyridine and the pyrrole motif.
Now I need a good pyridine starting material.
Yeah, like, yeah, I mean, you can use the dimethoxy and the aldehyde instead of the double bond. Like, you can disconnect through the double bond there between the ester, you know, and the pyridine.
Something like this?
Yeah. And the other one, the other motif can be ester CH2 N3 and go through nitrine.
Okay, so you're saying Hemmetsberger. Great. Lovely.
Yeah.
The key, folks, of Azaindoles is don't let the as intimidate you. Okay? If you don't forget, if you just pretend it's an indole, you're going to be fine. And that's also why we needed to learn 100 ways of making indoles, right? Because when, as we saw before in Tiffany's problem, when the nitrogen starts going here, you can't just do Fischer for everything. Great. How about this problem? This is an interesting one from about a decade ago. And we need some key disconnections for how to think about putting this thing together. It is a medchem project, so we probably want to put in the diversity in a stepwise fashion. And so who would like to take us through this one? Either Aaron or Camille, maybe any thoughts at all on this topic?
I guess I'm thinking, is it possible to buy the central is it indole?
Yeah, well, the first thing, that's always a good first thought. The first thing I really want to get from you, though, is what substituent do you think we can clear off of here as a med chemist that you think is fairly straightforward to just lop off?
The 2-amino position.
All right, let's get rid of that and then just make our life a little bit easier so we don't have to worry about that anymore. And let's just put E for ester there. We can always amidate it. All right, now things are a little bit simpler, slightly simpler. And if we're going to buy the intermediate we see here, let's think about what we need to buy. So give me some substituents here, Camille, for what are we going to buy or search in SciFinder for? We're not going to buy this. We need something a little bit simpler before we start buying. So tell me what to put at the 4, 5, and 6 position that is to start searching.
Can you put an amino at the 4 position?
All right. Now what do I put at 5?
I guess you could have the carbonyl there.
Okay, so Okay, and then what do I put at 6?
I guess you could have an alcohol.
Something like that, correct?
Yeah.
Well, the issue with this is, let me ask you a question. If I told you to make this compound versus telling you to make this compound, which would you prefer to make?
Okay, yeah.
Okay, that's the question to ask yourself every time you make a disconnection. I won't be there beside you on the test or in real life one day. And so that's the question you're going to be asking yourself after you make the disconnection. There's no shame to be had about making a disconnection that is not strategic. In fact, that is the best thing to do. The only way you get better is to show this is the logic of what I'm doing, and this is why this is not a good idea. So there's no shame in making the wrong disconnection. In fact, maybe there is a great way to turn that disconnection into reality, but we want to look at both. So let's consider for a moment what both may look like. What if we start thinking a little bit with Simona-like logic on a compound like that? Well, what she taught us is that this chlorine atom would look more like that. So far, that feels pretty good. How do we get that compound? Well, one could imagine this thing could come from treat this with a little ammonia. And then this thing could come from and now we're back at lecture number 4. This is lecture 4. Put those together. This will give you very cleanly that one. There's nothing else for it to do. And then treat that with trimethyl orthoformate. And then ammonia should be here. And then POCl3 should be here. Feels better, doesn't it? So for a job interview, what do you need? All you need to do is go in that room and say, well, I'm thinking you could either do this or you could do this, and I think this looks better. I could probably derive that from pyrrole. That's it. You're done. You got the job. They're not going to expect more of you than in a quick interview like that.
This is more, seems like a process route. They didn't use any potentially any cross-coupling or any other diversification.
Oh, they did lots of cross-coupling right here and right here. Amide bond formation, the 2 vectors that they want to explore are here and here.
I see, okay.
Yeah. But in this case, they want to retain this key active core. And you'll see this a lot. When we hear, well, the guest talk next week from Aaron Sather from Merck, you'll see that the reason there is a group that is in between discovery and process is precisely for this problem. A group in MedChem will have a key scaffold that they know they can't change anything in the scaffold, but they have 2 little handles on the side. Maybe one is amide, one is Suzuki, one is Buchwald, whatever. And so you need a way to get a kilogram of that key intermediate so they can make 1,000 analogs very quickly. And that's why you need a group like Aaron's to bridge the gap. You don't go to process chemistry for that problem because there's not a final clinical candidate to give them. But you need an intermediary. And that's why we're having a guest lecture next week from Aaron. Great question, Nick.
Yeah. Great, yeah, thanks.
So with that could you might have explained this, but could you explain the logic a little bit again with regards to starting from a pyridine core versus the pyrrole core? Because I feel like if you do the pyridine, you can do like Laroc or something like that if you have a halogen or like a Heck reaction.
Let's take it further. Let's say we're going to insist upon this route, and that would lead us down a road of something like this. That's the intermediate we need for Tim's Laroc strategy, right? And maybe this can be had from the corresponding N-oxide chemistry here, nitration, and then reduction to give the immunopurity. So if one put this on a test, I don't know. What do you think, TAs? Would we mark that off? I don't think you can. I don't think you can. I mean, it basically comes down to how expensive is this? Probably pretty cheap. And then how, well does the, you do the N-oxide, nitration, reduction, iodination, Laroc. Well, before you do the Laroc, you're going to have to throw that methyl group on there. You can't forget that. So you have to do methylation, then Laroc. So in terms of scalability, I would personally, even as a med chemist, prefer, assuming that I have to keep my core constant, prefer this dump and stir condensation chemistry from 1900s, because I can make buckets of this compound for all my colleagues to give us lots of SAR very quickly. Whereas this route might be something that you would do initially with a CRO just to get a proof of concept, but then when you want buckets and buckets of it, so that's why you need both. But it says you put that on a test, Tim, you wouldn't be counted wrong. But in an interview, you probably would want to come armed with the ability to suggest both of these routes, especially if the interviewer says we're already doing Laroc and it's not very good, it's very steppy. How do we fix it? Great question. Other questions? Well, we have a robust 20 minutes to go through two of my very favorite case studies in the history of Azaindoles. We'll start off with a cage match between Process and Medchem on this compound that was reported in by Merck, where we're going to talk about the logical ways of looking at this from the standpoint of a med chemist versus the logical ways of looking at this from the standpoint of a process chemist. So this is very exciting, even more exciting than that movie. All right, so for this, we need our designated medicinal chemist to help us, and we've got a team of medicinal chemists in this call. Maybe we can have Brendan versus Simona. So Brendan, you're the medicinal chemist. Give us some help on, first, what substituents would we want to remove first that are sort of innately primed for action here?
Just remove all the sort of extraneous.
What's the first extraneous thing to get rid of?
Sulfur, aryl.
Let's stop there. We want to remove the sulfur. So if we want to remove the sulfur, what kind of chemistry do I need to do to put that sulfur back in? Just tell me that while I'm drawing.
So I don't think you can do SNAR there.
Okay.
Unless you had an electron withdrawing group at the C2 of the indole portion there.
That's a great point. You hear what he's saying there? Don't do that on the test or in real life, please. Don't try to do SNARs on that.
But you can't. But can you do it if, like, let's say that chiral methylene ester there comes from a
ketone?
Like a ketone.
Perhaps. Yep. So let's do that first before we go on. Let's just draw that compound, because that is a good way of thinking about how we're going to install that exocyclic substituent. And so if we had a halogen here, yeah, we can't count that off in the test. That would probably work with the thiol nucleophile. But is there a way to do this without all the halogen stuff? Let's talk about Gewalt.
Yeah, I don't know if you can do.
let's have a sidebar on Gewalt. Can you remind me what went on with Gewalt? What was the substituents we needed for Gewalt? I forgot. So let's see. We had
nitrile.
what's that? Oh, what?
Nitrile.
Okay, so we had something like that. We had some sort of methyl group, and we added something into that. What did we add? You said what?
Like an ester.
What was the key atom we needed to add there?
S8.
Aha! Something special about sulfur. Now, going back here, we need an electrophilic. If I was to tell you to put an aldehyde here, what would you do? You'd say Vilsmeier, right?
Yeah, right.
If I was to tell you to put an X there, what would you do?
Just NIS, NBS, and PF.
Okay. So if I need to put a sulfur there, why can't I do this?
That's interesting.
Yes, and that's what they did. So we don't need anything there, folks. That's the answer. You can put that in a late stage, do all the interesting diversity explorations you want just by doing an electrophilic disulfide. That disconnection is so darn good that even the process chemists are going to adopt it. So take note, Simona, when you give your suggestion. Now, let's continue on with this great disconnection. You got us all the way to here, Brendan. And so now we just need a way to complete it.
Okay, sorry. So we're there.
Here, you got here for us.
Okay. Let me think here for a second. So what I'm seeing here is my sort of first thing I would draw would be cut the aryl nitrogen bond. And then you can trace that back. Then you can imagine having an aldehyde on the C3 position of the pyridine, and then that would probably just be dump and stir chemistry if you were to have like a chloride. Yeah, chloride beta to the aldehyde.
We're going to do what Debbie taught us before. Is that what you're saying?
Oh, that's not what I was saying, but
well, you have the aldehyde and you want to put and you want to annulate on an indole. The best way to do that is just Hemmetsberger.
Okay.
Right? And then once we get the product of the Hemmetsberger, we can do a Stille or Suzuki with something like that, or Negishi, and then reduction. Now, the only thing you haven't told us is how we're going to put the key carbon atoms in here to get that. That's the only thing that we're missing. So how do I go from here to here? I need these two carbons to be put in. And there's a nice way to do this. It uses some undergraduate chemistry.
I think here. Undergraduate chemistry. Okay.
Yep.
So I guess formally, yeah, you need to add the carbon into the carbonyl, and you need an electrophile for the nitrogen to attack. So
yes, great. So a good candidate for that would probably be this. We're going to get our Michael addition, heteromichael, to take place. We're then going to get the Dieckmann to take place with the ester here, and then decarboxylation, and you've got your 5-member ring. So that looks like a pretty good medchem route to me. I think the medchemists are probably pretty happy with that route. But then they tossed it over the fence to Simona, who had to clean up the mess. Obviously, process scale is not going to be so happy with the Hemmetsberger. They're not going to be so happy with Stille coupling or anything like that, followed by hydrogenation. There are certain things that they probably will be okay with. For instance, I mentioned already that disulfide, it's hard to beat that. You might even think that Dieckmann, gee, that's probably pretty hard to beat on process scale. So, Simona, what kind of things would you think about to revitalize the medchem route to make it suitable for multi-kilogram scale?
Well, I guess you pointed out that the Hemmetsberger wasn't going to be such a good option because of the azide.
Yeah.
So I guess would there be a different way to disconnect the ring, maybe the pyridine instead?
All right, I think that sounds really good. And so what we're going to do is, you still want to stick with this disconnection though, correct?
Yeah, I want to trace back to the ketone and I want to do the same cyclization.
So let's redraw. Let's basically get all the way to this compound. This is really the crux of it, because we're going to use a lot of the medchem logic. Just out of curiosity, Simona, how would you recommend we install that stereo center? Here. You're a process chemist.
Can you do hydrogenation with like rhodium or something?
Perfect. Okay. In process chemistry, 95% of the time, if you want to put chirality in a molecule, you're going to do it in one of three ways. First, resolution. And I know resolution is like a 4-letter word these days, but they still do it all the time because often it's really, really inexpensive to do that. The second one is going to be hydrogenation or reduction of some sort. And the third one is going to be biocatalysis. That's pretty much like 90% of it, okay? The other stuff is used on occasion, but 90 to 95% of the time, it's going to be one of those three sneaky ways of getting your chirality in there. All right, so Simona, how are we going to make this? You said you wanted to do annulation. You wanted to go from B to A, which is very intriguing. How are we going to pull that off?
Can you disconnect through some kind of 1,5 dicarbonyl logic?
Let's try 1,5-dicarbonyl and see where it leads us.
Or well,
That's 1,5-dicarbonyl, but it should give you a hint as to what we actually want to do. Which of the positions on the pyrrole, Simona, are innately activated to make a carbon-carbon bond, ready to go or ready for you?
C2, so the 5 position.
So C2 and C5, we know can come from some sort of Friedel-Crafts event. So this thought, if you continue to brainstorm on this thought, it's going to lead you naturally to this intermediate. That, and you just told us the answer for the other one. So what do we do now? This thing comes back from pyrrole. First step is Friedel-Crafts. That puts the one there after hydrolysis. With sodium methoxide, you get the ester. And then step 2, cheap. Methoxide is cheap. This simple amine here is cheap. Acid is cheap. Everything to get here is basically bucket chemistry for free. So great success as a process chemist. Look at that. I mean, probably they spent 10 human years of work between all the authors of this paper to come up with what you folks came up with in, I don't know, what was it, 5 minutes? You basically got the answer in 5 minutes of an entire program at Merck. So something is working in this class. All right, great. Now yeah, sure.
I have a question about the electrophilic sulfur step.
Yeah.
I was wondering if we can adopt sort of a Sworn type activation of like the sulfoxide derivative of that thioaryl.
Well, if you were to, the problem with the sulfoxide is there is no R group here. It's just that. So if you wanted to, this kind of compound would be the corresponding sulfoxide equivalent that you would make.
Mm-hmm.
It's not so stable. And we'll probably go straight to the sulfonate very quickly, which could even run the chance of getting you all the way to sulfonic acid, which is bad.
Okay.
It's easy enough, Nora, it's a great question, but it's easy enough just to take this thing which already wants to be the disulfide. Like,
Right.
sulfur, thiols are kind of like twins separated at birth, and they always want to be together.
Yeah, I guess I was just thinking that you're probably losing half of the molecule, but it may not matter.
Well, that is a good point. And so what sometimes people will do is take the aryl thiol and add equivalent of something like I2, which will generate dimer in C2, and then continue, and then you don't waste you don't need a full 2 equivalents.
I see. Thanks.
So if you were to use one equivalent, let's say 0.5 equivalents of this with another half an equivalent of oxidant, mild oxidant, you wouldn't waste any, Noor. Yeah, great question. Other question?
I want to make sure that is the Friedel-Crafts reaction more likely to happen on the C2 or C5 position?
C2, you mean C2 or C3? C5 or C3 on this compound? Which intermediate are you referring to?
I mean the last step.
The last step. So you're saying C5, here.
I mean the right step.
Oh, C2 goes first, and then once, as you know from the pyrrole substitution chapter, this is in the PCC book. First, after the first electron withdrawing group is here, the next one to go is going to be here.
If it is here, then why the last step would happen on C5 position rather than C3 position?
Because relative, no, so now you're talking about these two. This one is adjacent to an electron withdrawing group, and this one is distal to it. So for electronic and steric reasons, you're going to favor going again at C2. And also in the book, you can find that answer where if you have a C2 and 5 electron withdrawing group, the next one that is going to be electrophilic is at that position. But yeah, it's a great question. That's the order of events. First here, second here, third here. All right. We have
So
7. Yep.
I'm sorry, I just wanted to quickly ask. It's generally not really true that it's easier to build a pyridine onto a pyrrole, right? It seems like it generally could be the case.
Well, as I said before, 70% of the time, it's going to be easier to throw a pyrrole onto a pyridine. And for the purposes of medchem, often that's the way to go. But when you know what your target is already, this is an example of where it makes sense to build the pyridine from the pyrrole because we don't need any diversity. Imagine how terrible Simona's route would be if it was medicinal chemistry. Every time I want to put another alkyl group here, I have to go all the way back to the beginning. That would be horrific. You would be fired.
Right, I see. Yeah.
Yeah. All right, great. We got to move on because I only have 6 minutes left and we have to cover this. So this is sort of the climax of this lecture, the most exciting Azindole in recent history, the crowning achievement by the BMS process team led by Martin Eastgate and colleagues, reported in 2017 with a lot of fireworks, 9 back-to-back OPRD papers. The entire issue on this compound. I spent many years in the virtual trenches with these amazing chemists brainstorming, and it was fun because it started off back at the Wallingford site at Bristol Myers in Connecticut, where they were doing med chemists. A lot of really cool chemistry came out of that, as I'll show you in a moment, and then transitioned to New Brunswick, where they had to start completely over again. But a lot of beautiful chemistry was developed by both the process chemists and the medicinal chemists, and I'll show you what that was. So in the remaining 5 minutes, we need now 2 folks who can spar against each other. And maybe we can get Ellie from the medicinal chemistry side and Kelly from the process chemistry side to help us decipher what we can do to put this together. So Ellie, can you give us a quick disconnection? Let's remove some substituents as fast as we can to get to something good.
Yeah, I was thinking of removing the diketone off of the indole side.
Awesome. Let's get rid of that. Anything else you can quickly get rid of?
Probably would want to get rid of the triazole.
We're going to get rid of that at some point. Anything immediately? You want to carry this through the whole synthesis as prodrug?
No, yeah, you can also get rid of that.
Get rid of that really quick. All right, now we have to figure out a way to put that together. And as you mentioned before, it would be probably a really good idea to get rid of that triazole. We might worry about the regiochemistry of the SNAR, but that's a topic for another time. And now I need a quick way, Ellie, to put this thing together.
Yeah, I think you could do like Laroc or maybe Madelung even to.
Great. Okay, so we can imagine this kind of thing comes back from a variety of different precursors. We can imagine something like this, X equal to bromo or methoxy. All of these kinds of variations were used. We'll put a, sorry, a chloro goes there. We can imagine, so this would treat with DMA, and then you would get the product. We can imagine maybe a Bartoli would work just fine. So now we're just going back to the essentials handout that you can use on the test, and you could look at the name reactions for making indoles, and you could apply them one by one here without any problem. So all of this would give you pretty modular direct access to the Azaindoles scaffold that could be then interrogated with regards to the alkoxy substituent, with regards to the heterocycle, and with regards to the Friedel-Crafts amide eventual oxalate type group that you've got here. All those things can be systematically done in a great way, thanks to Ellie. And now we need to turn to Kelly, who needs to fix all the problems associated with Ellie's route. Now, was there anything good about Ellie's route that we can use from the very beginning, just like we were able to take some sneaky things in the previous route and use them in process?
I think the way that she put together the Azaindoles looks pretty good. And I think I might also install the heterocycle by cross-coupling.
All right, so you mean a Friedel-Crafts type reaction. Let's first bring it back to an intermediate that makes a little bit more sense.
Yeah, I don't want to do the N-alkylation last.
So the process chemists recognized that probably they could use Ullmann conditions with ligand control and somehow optimize for the alkylation to take place there. So that part would lead us back to the simple bromo compound. Now, with that bromo compound in hand, you could imagine doing cross-coupling. You could imagine doing Bartoli. There was a period of time where I would come and there was a competing sort of internal team at BMS doing Bartolis, and it never made any real sense for a lot of people because those yields were never above 50%. And it's hard to imagine ever doing Bartoli on large scale and getting a very good outcome from that. So the cost of goods was also a big concern because the dose of this compound was very high. It's about 1 gram or so per day. So the anticipated cost of good was extraordinarily high and necessitated that we start from almost crude oil. So we've got A and B here. And it looked like at the time, all of the cross-coupling and ways of annulating on a pyrrole had been exhausted. And from a cost of good perspective, there simply was nothing good to do there. So going backwards, they recognized that that bromine here could probably be installed through some sort of Reiser reaction. And we're going to put on here a SO2 pH group for reasons that will become clear in just a moment. So this could be done by using methyl trioxyrhenium, or MCPBA works fine, and then treating that with PIBROP. Interesting chemistry that we had worked on with BMS in the very first collaborative paper we had with them many years ago. A nice way of taking those N oxides and rearranging them to the 2-bromo azindole or pyridine or quinolines. Okay, now the key disconnection here, we need to start thinking like Simona again, and that is thinking about how we might annulate A starting with B. So in thinking about this, you can imagine if we bring it back, if you treat this with methane sulfonic acid and trimethyl orthoformate, that's the product you get by way of the intermediate being this compound and loss of tazol to aromatize. That sort of brilliant stroke of logic there leads you back to this intermediate. And now all we need to do is start with that, which then comes, as we learned in lecture number 2, comes from that. Friedel Crafts taking place selectively here with the corresponding acid chloride. Gets us to here. We then treat this with a tazol nucleophile. Followed by deformylation of that group, gets you to here. You then treat this with simply with formaldehyde or an equivalent of that. That does your Friedel Crafts, which takes place here. And then upon workup, you get your ketone, which can be aromatized. So they get their, think about this, their methoxy is coming basically from methanol rather than using methyl iodide or using a cross coupling to put the methoxy in. That's part of the brilliance of this approach. Now, this is a very long story, and so we don't have time to go through all of it today, but if you want to take a look at an overall summary, we wrote a little opening to this 9-paper issue, and it goes through the entire timeline of how this was discovered, including a lot of really cool as-indole methodologies that we currently learn in class today that we've covered before, and those things arise from the medicinal chemistry department in Wallingford, led by the famous Nick Meanwell and John Kadow and many of those pioneers in virology. And here is the medicinal chemistry synthesis, very similar to what we talked about. And then the 9 publications that are shown here are summarized in a very quick fashion. So if you don't have time to read all 9 papers, you can take a look at this editorial that we wrote that summarizes this landmark contribution to medicine. So with that, we have completed on time all the discussions of our first exposure to fused heterocycles. And what remains before the midterm is a discussion of course, quinolines, and then maybe the most difficult part of the first half of the class will be a discussion of naphthyridines, some of the hardest heterocycles to figure out how to make. So with that, have a great weekend, folks, and we will see you on Monday.